In 1964, a physicist by the name of Peter Higgs took some ideas that were floating around at the time, added an insight or two of his own, and proposed that there was an energy field that permeated the entire universe. This energy field is now called the Higgs field. The reason he proposed this field was that nobody understood why some subatomic particles had a great deal of mass, while others had little and some had none at all. The energy field that Higgs proposed would interact with the subatomic particles and give them their mass. Very massive particles would interact a lot with the field, while massless particles wouldn't interact at all.
Imagine an infinite field of snow extending throughout all of space. Flat, featureless, going in all directions. Maybe the middle of Siberia. Now imagine that you're trying to cross this field of snow. So maybe you're a skier and you skim across the top. That's like a particle that does not interact with the Higgs field. It doesn't sink into the snow. It goes very fast. That's like a particle with no mass traveling at the speed of light. But maybe you've only got snowshoes. In that case, you sink into the Higgs snow field. You get less speed than the skier, less than the speed of light. That's like a particle with mass because you are interacting with that Higgs snow field. And then finally, if you've just got boots on, then you sink deeply into the snow. You go very, very slowly, and that's like a particle with a big mass.
The lightest of the familiar subatomic particles is the electron, while in the subatomic world, the king of mass is the top quark. It weighs about as much as an entire atom of gold, about 350,000 times more than the electron. I'd like to stress that we believe the top quark is not more massive because it's bigger. It's not. In fact, we believe that both the top quark and the electron are exactly the same size. Indeed, they both have zero size. The top quark is more massive than the electron simply because it interacts more with the Higgs field. Actually, if the Higgs field didn't exist, neither of these particles would have any mass at all. Now, in the press, you don't hear about the Higgs field, but rather the Higgs boson. How are these two things related? The Higgs boson is the smallest bit of the Higgs field. To understand how that works, we should again return to water. Everyone knows what water is. If you're immersed in it, you know that water is everywhere. It's a continuous medium, and there are no holes in it. We also know that water is made of molecules, specifically H2O. If you hold these two ideas in your head with the realization that water consists of countless individual molecules, you can now begin to appreciate the Higgs boson. The Higgs field that gives subatomic particles their mass is made of countless individual Higgs bosons, just like water is made of individual molecules.
But a great simplification was made when we realized that all the atoms are just made out of three particles, the protons, the neutrons, and the electrons. And just by adding more protons, more electrons, we get a different element, a different type of atom.
In principle, you can build a very simple universe with just protons, neutrons, and electrons.
But it became much more complicated in the beginning of the 20th century when we found many, many new particles from cosmic rays.
There wasn't really a system established to organize this zoo of particles. At the beginning, there were only 3 quarks. Then a 4th, 5th, and 6th quarks was predicted and then discovered, and this gave us great confidence in the model. In addition to these quarks, there's another set of fundamental building blocks of matter, the so-called leptons. They are composed of an electron, their heavier cousins, the muon and the tau, and their neutrino partners. In addition to the fundamental building blocks of matter, the Standard Model also incorporates the fundamental forces. The exchange particles of the weak force are the W and the Z boson. The weak force explains the energy production in the Sun and is responsible for the radioactive beta decay. The electromagnetic force acts on charged particles. The corresponding force carrier is the photon. The electromagnetic force is responsible for propagation of light or for the fact that a magnet can pick up a paperclip. The strong interaction acts on the quarks. The corresponding force carrier is the gluon. The gluon literally glues together the quarks in the neutrons and the protons, and it holds the nucleus together.
The standard model is extremely successful, and it has predicted all the phenomena we have seen so far at the microscopic level.
This is a beautiful theory. It is self-consistent, it's predictive, but it's incomplete. There's one last missing piece of this puzzle. That's the Higgs boson. It's the holy grail of particle physics.